In this session, we're going to be talking about complex lipids. And the two primary complex lipids we'll talk about is the triacylglycerol structure, which is our glycerol backbone, with our three fatty acids linked to the carbons of the glycerol backbone in an ester linkage. The other structure is the phospholipid, more correctly called the glycerophospholipid, three-carbon glycerol backbone, as in the triglyceride structure. And here we have two fatty acids linked to the number 1 and number 2 carbons by the ester linkage, of course. And on the number 3 carbon, we have a phosphate group that is connected to what's called a head group. And we'll talk about that in a second. Now, the biosynthesis of the triacylglycerol and glycerophospholipids follow a common pathway up to a certain point. And the start of this pathway is going to be glycerol 3-phosphate. Now the glycerol 3-phosphate, I think you'll probably recall, hopefully, where this comes from. We are in the fed state, and that means we have substrates moving down through glycolysis. And so remember, the glucose enters the cell. It is processed down to glyceraldehyde 3-phosphate plus DHAP, dihydroxyacetone phosphate. Now recall, DHAP can be converted into glycerol 3-phosphate by a simple one-step redox reaction, which we'll be using NADH to reduce the DHAP into glycerol 3-phosphate. So the glycerol 3-phosphate that is going to be the backbone of triacylglycerols and glycerophospholipid comes from glycolysis. Now the first step in this reaction is we are going to add a fatty acyl-CoA group. Now remember, this fatty acyl-CoA, this is a high energy bond, so this is the bond here. Energy is going to drive this reaction forward. And because we are in a fed state, this is the product of the fatty acyl synthetase enzyme that is going to conjugate CoAsh onto fatty acid and hydrolyze ATP to introduce the energy we need for the reaction. So the first step of this reaction is going to add the fatty acid onto the glycerol backbone to give us our monoglyceride structure. And this is an acyl transferase enzyme, fatty acyl transferase enzyme. The next step of the reaction is going to be the same reaction with another fatty acyl-CoA group, and then we are going to add our fatty acid onto the next carbon. And what we generate here is the common denominator between triacylglycerol and glycerophospholipid synthesis. And this is called phosphatidic acid. This common precursor now has two different directions it can go. The first direction it can go is into triacylglycerol synthesis. Now, in triacylglycerol synthesis, remember, there's only a couple of organs that will be performing this reaction because they're the only ones that have the next series of enzymes to do this. Fatty acid synthesis occurs in the liver in the fed state, and triacylglycerol is the product of that. So this will be occurring in the liver. Storage of fatty acids in the fed state are in the adipocyte, and the adipocyte will also be constructing triglycerides for said storage of the fatty acid. So liver and adipocytes will be the two primary organs that will be performing this reaction. So in this reaction, the first step is going to be removing the phosphate group from the number 3 carbon. This enzyme is called phosphatidate phosphorylase, and this enzyme will be removing the phosphate group. Phosphatidate phosphatase. Now, what we will have then is a free carbon for a fatty acid addition. Then the next structure can be an acyltransferase to add one more fatty acyl-CoA onto the structure to give us our triacylglycerol structure. The other direction we can have here with the phosphatidic acid is to add a head group. Now the head group can come in 3 primary forms, although there's additional ones we'll talk about in a second. And these head groups are going to be added onto the phosphate group. The 3 primary head groups that will be added will be phosphatidylserine, and I'll explain the CDP in a second. And phosphatidylserine is going to be a potential head group. The other potential head group is phosphatidylethanolamine. Here's our ethanolamine structure. And then the final head group will be phosphatidylcholine. Now these head groups, notice, have charges to them. So these are the head groups when we talked about the bilipid membrane, and we have our structure that is typically drawn. This is called the head group. This is the hydrocarbon tail. So the hydrocarbon tail will be in the intramembrane space. This will be the hydrophobic bilayer domain of the membrane. The head group will be in charge, will face either the outside or the inside of the cell, being soluble and bonding with the aqueous environment. So these head groups have to join on the phosphatidic acid onto this phosphate group. So the phosphate will be the link between the head group and the glycerol backbone. But as our theme we've talked about before, small molecules that want to join onto larger molecules need to have their own energy. So this is essentially a high energy structure. Now, where do these come from? This is the serine group. Notice the serine can be made into the ethanolamine by a simple decarboxylation reaction. So removing this carboxylic acid group will convert the serine into ethanolamine. Once we have the ethanolamine structure, we can now convert the ethanolamine into our other head group, which is choline. And this is going to be done in 3 separate reactions using 3 times an accessory molecule called SAM, which stands for S-adenosylmethionine. We'll talk more about SAM, the synthesis of SAM, but SAM is involved in 1 carbon transfers. And so to convert ethanolamine into choline, we are going to do 3 individual 1 carbon transfers, 1 carbon being the methyl groups. And here we have now 4 bonds onto nitrogen, which gives it a permanent positive charge. So the final step to convert phosphatidic acid into a glycerophospholipid is to use this high energy structures with the CDP and added onto the phosphatidic acid. So as an example, I'll draw ethanolamine on what this will look like. The final structure. And here we have a glycerophospholipid. This is called phosphatidylethanol amine.